Boom. Okay, I actually thought this script was going to be a little bit longer to create this form, but because I've done something similar to this in a different project that I'm going to make a video about, but I found a better process. So what's going on here? How the heck does this thing work? Well, I think you can see that there's a little bit of a complexity here because the gradient distance is not consistent around this shape. In this part of the model, the gradient distance is a lot longer than the gradient distance here, which is what we can see in this picture. Like the first thing I noticed was that this is not like a constant gradient. This is not like an attractor point type of script. If there's an attractor point here, then the gradient would be more consistent around all the edges. But it's not consistent because this is a very long gradient, and this is a kind of a shorter gradient. So that's what kind of makes this script a little bit complex. So let's go over how this thing works. Well, I'm gonna hide most of this stuff. We're gonna start off at the very beginning. So what I knew instantly is that we needed two shapes to be able to define what's going on here. We need a shape to define the overall bounds, the overall boundary of the light points, the light sources. And then we needed another boundary to define sort of this shape where I can see mostly like a 90% fill, a 90% fill rate of these lights. And then there's this part here where it kind of tapers off, and it tapers off just at the edges. So I knew I needed this other shape to kind of define that boundary region. So I'm gonna put it like right about here, right? Does that make sense? So that's kind of like my approach to this whole thing, right? And so the first thing we're gonna do is we're gonna create this outer rectangle. We're gonna create this inner rectangle, and we did that in Rhino. And so those things are obviously those can be reshaped, resized because this is a fully parametric script. And we divided it into we used the divide surface component, and we input a curve into the divide surface component. Sacrilege. No, it's not. It's fine. You can do that. We're allowed to do that. We can break some rules. Yeah, we put a curve in the surface component. So whatever. And go for it. Break some rules. You know what I'm saying? It works. So we're going to do it. And so we put that curve in there. It's a rectangular curve. And the component accepts that. That's cool. I'm good with it if you're good with it. And we divided it. Now looking at it, we probably should use a different U and V count because this is not a square, but I'm not gonna worry about it. Whatever. If you want to refine that detail, go for it. So now we have these points, and I just flattened them because we don't need the grafted data, right? As some of you might be aware, if we open up our param viewer, boom. Okay. If we open up the param viewer, you can see that we have a separate branch for each row of points. And so I'm just going to flatten that because we don't need that data structure. And then I'm using this curve to define which points are inside this curve. We're going to treat these points differently than the points that are outside of this curve, right? So we're going to use point in curve. That's cool. We're good with that. Okay. Point in curve is going to give us some relationship, a list of relationship numbers, 0, 1, and 2. 0 is outside, 2 is inside, 1 is coincident. And be careful with coincident. It needs to be perfectly coincident, and if it's out of tolerance by a tiny bit, it won't be coincident. And then we can use these two components to basically separate out these points. That's kind of like what I did here, right? So because 0 is outside and 2 is inside, so these are going to be designated 0, and these ones are going to be designated 2, right? And so anything that's not 0 is going to be a true. And so here we have this cull pattern that's going to be 0, 0, 0, 0, 0, 0, 0, 0, 0, and then at some point it hits a 2, and that means that we're going to keep those points. And so we've separated it out. So in this component, we've culled all of the zeros, right? So we culled all the 0 points. But in this component, we went in here and we used the invert IO modifier. If you haven't seen the IO modifiers video, go check that out on YouTube or Instagram, Parametric Philosophy. The invert IO modifier. So we flipped those results. Instead of keeping the inside points and throwing out the outside points, we kept the outside points. So I'm just using these two to split it up. And so let's take care of these inside points first because they're easier to take care of. There's not too much going on here. I'm just looking at this. There's not really any significant pattern. They're not like reducing as they get to the edge. They're just sort of there's just a few of them that are just kicked out basically. So to me that just looks like a random reduce. Okay. So with the random reduce, all we're going to do here is we're going to count. So random reduce needs a list of points to reduce, and it needs the reduction number, the number of items to remove. Now, I always thought that this should be like a percentage. Maybe I should just make my own user cluster. I should probably do that, because I pretty much always use a percentage for this one. So what I've done here is I've counted the number of components, the number of points, 748, and then I multiplied that number by a number slider to give us the number that I want to remove. So if it's, this is like 11%, so we're going to remove 83 points, all right? So that's a reduction number, and now, so we removed, we removed like 11% of the points, and that gives us an effect that looks very similar to what we have here inside this hypothetical boundary. So we've taken care of the points inside that boundary. That's fine. We've taken care of that. So let's just hide that for now. Now, this is the part that gets a little bit more complex. Ooh, I don't know. This is an interesting concept that took me a bit of time to figure out. I kind of, like I said, I kind of figured out a simpler way to approach this, but I worked on this for a long time in the past. A few months ago, I guess it's been kind of like stewing in the back of my head, and my subconscious, the strength of my subconscious mind just worked on this problem in the back burner for a while, because I'm pretty happy with this result. But how to go about, they say you don't really understand it if you can't teach it. So right now, I have to teach it because my ego wants to tell you that I can understand it. So basically, what I'm trying to do here is that if there's a point, like this point, I'm isolating this point because basically we're talking about these points. We're saying, how do we create a gradient where statistically the probability of these points existing is almost 0, and statistically the probability of these points is almost 100% chance that these points are existing. But we have to do the same thing all the way around this shape. So these points have to have an existence a probability of 100, and these points have to have a probability of 0. So it's difficult because the distance, like I said, the distance of that gradient is changing, right? So the way that I'm trying to organize this idea is that if we isolate one point, like say this point, we're saying that it's about, a certain distance away from this curve, and it's a certain distance away from this curve. And so if it's like 1/3 here and 2/3 here, then it has about 66% chance of probability of existing, right? And that would be the same thing as if this point was here. If it's about if it's about 1/3 and 2/3, it has about 66% probability. So what I'm doing here is I'm measuring, we're using this component here, which is curve closest point. And I'm measuring the distance from this point to this curve. And I'm also measuring with this other, the same component, duplicated. I'm measuring the distance from this point to this curve. And let's keep going here. I take these numbers and I round them. Just, you don't really need to do this. You don't really need to round them, but I'm getting like a lot of numbers that are very close to 0, and just kind of bothers me. Just kind of like messes with my OCD. So yeah, again, you don't really need to round it, but I just like to round it so that we have some cleaner numbers just to look at. 0, 0, 0, 0, 0. And so what I'm doing then is I'm adding them together so that this distance plus this distance, the distance from this point to this curve, plus the distance from this point to this curve is the overall distance. So we know what our overall distance is, and then we know what the relationship is between the distance of this to one curve relative to the overall distance. And that gives us a percentage, right? Hopefully that makes sense. So again, I'm just going to say that again. If we add this distance plus this distance, then we have the overall distance between each curve, no matter where this point is in this whole shape. And we have the overall distance between the two curves relative. We still have the information of this point to this curve. So we have the distance of this point to a curve relative to the overall distance. And that's going to give us sort of a percentage of how close it is to the 100% curve versus how close it is to the 0% curve, right? So we add those together, and then we have to put it through the graph mapper. We have to put that data through the graph mapper. Okay, so we actually don't even need to use the graph mapper, but the graph mapper is going to allow us to modify the gradient, the culling gradient pattern. So we're just using the graph mapper to allow like further customization. But the graph mapper in some ways can help us visualize what's going on. But you know, okay, so we understand that we've created this part of the algorithm, to understand the relationship between the overall length between the curves relative to where this point is, that overall length relative to the distance from the 100% curve to the point, right? I'm calling this the 100% curve. I'm calling this the 0% curve, right? So we understand this distance. We understand that it's 1/3 of here relative to the overall distance between the curves, right? And then when we put this number through the graph mapper, we've remapped it. We've remapped every one of these relationships down to a domain of 0 to 1, so that we can put them all through the graph mapper. So we have all these domains that we've remapped to 0 to 1. And when this number goes through here, because it's like 1/3, right? It's going to come through here, and it's going to come out as 1/3 because it's a linear graph mapper. The y is going to equal the x because of this slope. But again, we have the graph mapper so that we can modify that relationship. And now that these numbers coming out of here are going to be from 0 to 1, now if we create a set of random numbers, and we've used the list length component to create just as many random numbers that are also from 0 to 1. Since the random numbers have no influence, the random numbers are just randomly any number from 0 to 1. That means that the closer that this number is to 0, the more likely that this is going to come out to be false, because this is a smaller than component, okay, or larger than component, sorry. This is a larger than component. So if these numbers are coming out, if this number is 0.5, okay, if this point was smack right in the middle of these two curves, right, this number coming out of the graph mapper is going to be 0.5, because it's going to go x is 0.5, so y is going to be also 0.5, okay? And therefore, this random number, the random number generator, is generating random numbers between 0 and 1. So it's going to come out, so it's going to have an equal probability of generating a number larger than 0.5 as the probability that it will of creating a number smaller than 0.5. Okay? And so when we go, is A larger than B? If A is 0.5, then there's a 50-50 chance that A is going to be larger than B. So whether this is true or false is about 50-50 if A is 0.5. And if A is 0.25, then suddenly now there's a 25% chance that A is going to be larger than B. So now there's going to be 75% chance that this is coming out as false. Okay? And if this point is 75% of the way from 100% to 0%, then there's a 75% chance that A is larger than B. And so there's a 25% chance that we're going to have a result of true. That was probably very confusing. So I'm going to work on how to explain this later, or at some point I'm going to have to figure out how to like create some type of lesson here. But hopefully that kind of made a little bit of sense. I might get Liam to see if he can like help me make a diagrammatic explanation of this concept. So because we have all these, we had to create this relational set of data that says where is this point relative to the overall length. Then we ran it through the larger than component with a set of random numbers to assign it some type of probability of existing. Then we can use the cull pattern component, and boom. And now anything that's close to this curve has a 0% chance of existing, and anything close to this curve has a 100% chance of existing, right? And the reason that we used the graph mapper is because we actually don't want these points to have a 100% chance of existing, because we already culled these points. We know that there is not any place in this whole pattern that has a 100% chance of existing, because we have this cull reduction, right? This pattern reduction. So I actually don't want these points to have a 100% chance of existing. I want them to have like a 90% chance of existing, because that's what we have here. That's what these internal points have, right? So these points inside the curve have. So I'm going to modify this graph mapper to give it less chance, to give these points a reduced chance of existing. So I'm going to pull that down to like 90%. Push that to 0, put this to like 90. And that's just about exactly what we want. Now we can see some of those points are disappearing, and then if it's going to fit perfectly into the rest of our pattern. If we don't see these curves, you're not even going to tell. You're not even going to be able to tell where those curves are. So that was a little bit confusing. Hopefully I can come back to this and clarify this a little bit if necessary. But let me know what you guys think about this concept, this definition. Let me know what you think of this project. I think it's kind of an interesting interior lighting experience. So I thought it'd be interesting to try to model that definition. And I hope you enjoyed this quick little video. Take care, my friends. Keep designing your stuff. Peace.